Okay, so here we were, and the sum of the vectors a and b start at the two tips right over here and head towards the two tails. So this would be the resultant vector a plus b. All right, why don't you try using the parallelogram method to do the next couple of problems and pause, and we'll go over them in class when I'm back. All right, well, there's no such thing as a vector subtraction. We can add the opposite of a vector. So if a vector and its opposite are added together, the resultant vector would be the 0 vector, which we can denote with just the number 0 with a vector symbol over it. So literally, it would just look like 0. That would be a no, 0. And it would have that vector symbol over the top of it. So vector. So for example, what we're saying there is if this is b, then negative b goes in exactly the same distance but in the opposite direction. So this guy right here would be negative b. And they undo each other. It's like if you walk 3 paces forward and 3 paces back, theoretically you are in the exact same place. So if I find b minus b, and what we're doing here with our, the way we add the two vectors, so basically what we're saying here is that if we start here, start at the bottom, and then we travel vector b up, and then we travel vector b back, right? Theoretically, we also end in the exact same place that we started in, and so therefore we have gone nowhere because it's our start and our beginning. A minus b would say, okay, well now we're going to travel vector a, right? So we're going to travel vector a, which we got right here. So that's vector a, and then we're basically adding negative b. So this really means vector a. So it really means vector a plus negative b, so the opposite of vector b. All right, so we said the opposite of vector b would start here and go back. So now if I go ahead and I take that vector, this would be like a and then negative b, and so my resultant vector is going to begin at the tip of a and end at the head of b. So this vector right here, this dotted vector, would be a minus b. All right, we can also multiply vectors by a constant. A constant, so something that just has magnitude but no direction, is called a scalar. And doing so does not change the direction, it just changes how many of those vectors get added together. So let me just kind of give you an example. Here's x right here, and if I multiply x times 3, it just means I'm going to travel 3 of those. Right, so here, I'm actually going to, you're going to wish you had this on your paper. I am going to make clones of it. In fact, right over here, I'm going to make it an infinite clone. All right, so traveling 3 x's would be like, oh, I'm going to have to move them down. 1, 2, and then, oh, and one more. Oh, I did not grab it. Oh, that's annoying. All right, and then one more. There you go. So this would be 3x, negative 2x. So instead of going this way, it's going to go in exactly the opposite way. So negative x would be like right here. And I've got one of those. And then another one. And that would be negative 2x. And then negative half an x is kind of exactly what you think. It would be going halfway down. We're going to have to use our approximation. You could technically measure this, but negative a half of x, I would say, is about what we see right here. So negative 1/2 of x. All right, so if you can go ahead and try to do this, 3x minus 3/4 of y, that's doing exactly what you would think. And then the ones below it, try and fill those in, and we will check those when we go over these. All right, so parallelograms are a great way to relate vectors in the plane to one another, because some of the properties of parallelograms that we learned in geometry are really very similar to what we want for parallelograms, for vectors. So hopefully you'll remember that opposite sides are both congruent, meaning the same length, and parallel. And this is good because it means that opposite sides could either be the same vector or negative vectors of one another, depending on what it is we want to do. And the diagonals do something interesting. They bisect each other. And the reason that's interesting is because it means that we are able to get other vectors inside the parallelogram that have a different direction. So here I have below, like I said, just kind of some parallelograms. They're always quadrilaterals. They have two pairs of parallel sides. Their opposite angles are congruent. That's going to help us next time when we do some more math with our vectors. The opposite sides are congruent. Diagonals bisect each other, and actually opposite or adjacent angles are supplementary, meaning they add up to 180 degrees. All right, how's that going to help us? Well, here I have this kind of pre-existing diagram. It's a parallelogram, which means the opposite sides are congruent. So what we're kind of getting at here is, like, let's say we travel from E to T, and we called that vector 0 or vector O. Not vector 0, vector O. That's the same as traveling from R to P because it has the same magnitude, right? Because they're congruent, and it has the same direction because they're parallel. So vector O over here is also over here. We could use that. And vector, for example, R, from R to S, is the same as S to T because those are congruent. Those are, because the diagonals have been bisected. So what I mean by that right here is, so we're going to travel these vector sums, and we're going to use the parallelogram to come up with the answer. So we're going to start at the beginning of F, and then we're going to add O. So we're going to start here. This is our start. All right, we're starting here. And we're going to travel all the way along vector F. And then we're going to travel along vector O. Well, vector O is over here, but we said that that's the same as from R to P. This is also vector O. So if we travel all the way down from R to P, that means that we end right here. So we started over here at point E. We ended at point P. What vector would get us there? Well, D will get us halfway there. So 2D, 2 vector Ds will get us the entire way there, because this is vector D, and so is this. So we've got 2 vector Ds will get us the whole way there. All right, I want you to try the other 3 problems, and we will definitely go over those afterwards. All right, vectors, we see them in nature a lot. It's one of the reasons why you learn about them so much in physics. And I do have a really cool video here that I could show you about somebody walking in wind, but I'm going to show you in class. But basically what I want you to get at is, if you've ever walked on a windy day, your vector, what you're trying to do is you're trying to walk in one direction, and the wind is maybe blowing in a different direction. And if those are opposites of one another, it ends up pushing you maybe back or making you walk slower. Or if those vectors are in the same direction, it means that maybe you're going to go faster in that direction. And so wind is a huge vector in nature that definitely affects a lot of the things like sailing and walking and all that good stuff. All right, how do we do these vector word problems? So we've got Heather is pushing the handle of a lawnmower with a force of 450 newtons at an angle of 56 degrees with the ground. So they kind of gave us this nice diagram. Draw a diagram that shows the resolution of the force that Heather exerts into its rectangular components. Okay, what do we mean by this? Well, basically, these are going to be our nice right triangles. So we've got our 450 newtons, that's the magnitude. Here's the ground. Okay, that's supposed to be flat. We have 56 degrees here. Right, so if we imagine that two things are happening, when we push something forward, we have a vertical force, which I'm going to call y, and we have a horizontal force, which is pushing it forward. So it's kind of pushing it down and forward at the same time. And so what they want us to do, find the magnitude of that. They want us to find how much force is being pushed down and how much force is being pushed forward. So here's our right triangle. And remember, SOHCAHTOA, trig is coming back in a big way for us. SOHCAHTOA is going to help us understand a little bit more, find these other horizontal and vertical components. So when I want to find y is opposite that angle that we are given. And so we're going to use sine because we have opposite and we have hypotenuse. So to find y, I would say that the sine of 56 equals opposite, which is y, over hypotenuse, which is 450. And then we multiply both sides by 450. And that is what we're going to type into our calculator, 450 sine 56 equals y. All right, so I'm going to go ahead and do that. Just make sure that you're in degrees. And on my calculator, that came out as 373.066. So y looks to be 373 newtons. So that's the vertical component. And then to go ahead and find out the horizontal component now, we've got x, which happens to be adjacent to that angle. So that's going to have us use cosine. So I have the cosine of 56 equals x over that 450. We're going to multiply both sides by 450. And we're going to type that into our calculator and get back what that happens to equal. Which looks to be 251.6. 251.6 is what x happens to equal. So that's our horizontal force. All right. So just I want to do one more example with you, and then you have the rest of the packet to finish. So a swimmer heads perpendicular to a 3 mile per hour current, and her speed in still water is 2.5. We want to find the actual speed. So right here we have this diagram. If you don't like doing the tail-to-tail method, like making it into a parallelogram, you are welcome to turn this diagram into something that's a little easier to understand. For example, I kind of think of it like we're traveling at 2.5 miles per hour. So this is my 2.5. And then the current so I kind of like the triangle method or the tip-to-tail method. So the current pushes me down at 3 miles per hour. So that's our 3 miles per hour. And the reason I like this method sometimes a little bit more is it's easier to see that this is the resultant vector that we're looking for. Here it's kind of easy. It's like sometimes a lot we want to connect the two heads together, but that would not be correct. So this is the one that we're looking for. So it says find the actual speed and the direction. I'm going to do this one with you. So for the actual speed, right, we can say that we're looking for this value right here. And since this is just a right triangle, and we know it's right triangle because across a river and down a river are perpendicular, so we can just use Pythagorean theorem that 2.5 squared plus 3 squared equals x squared. So go ahead and you can use your calculator for that to solve that. 2.5 squared is just 6.25 plus 9 is 15.25. So we have 15.25 equals x squared. And then we take the square root of both sides. And so x will equal 3.9. So that's how we find the magnitude. To find the direction, what we're looking for is we're looking for this angle here. So I'm going to use the sides that they gave us, this 3 and the 2.5, as opposite and adjacent. And so if we go back and we use our tangent again, that tangent was equal to opposite over adjacent. So tan of this angle, theta, equals opposite 3 over 2.5. And so now that we're trying to undo the tan or find the tan, I'm going to have to take the inverse tan. So I'm going to have to take the inverse tan of 3 over 2.5. Alright, so 3 divided by 2.5 gives me some kind of crazy decimal, 1.2. And then I'm going to take the inverse tan of that, so second tan, and it's 50.194. So this angle right here, theta, is 50.194, and that's a true bearing because if we think about this as being north, then that's 50.194 from north. All right, so go ahead and answer the rest of the questions. You have a couple more things to do and finish up this packet for homework. Thank you. Bye.